tutorial today. Do we expect it to be in
Yeah,
the
yeah,
tutorial?
yeah.
Because next week I will be out of Portugal and I would like to let you know.
Okay, we can talk to it so now we're going to start using Keras, the API, and not implementing things at the lower level as before. And we're going to start looking at different layers, which are these convolutional layers for convolutional networks. I'm going to start by talking a bit about what is a convolution, and then we're going to see how to build convolutional networks using these layers, pooling, and the idea of also having fully convolutional networks for some particular applications. And for today, we are going to do an exercise using the Keras API, the sequential API, to create convolutional networks for classification. So first, mathematically, a convolution is this. This is a convolution between two functions, f and g, at time t, is the integral of the product of the two functions, but one of them inverted, so the symmetric of one of the functions, and this is commutative, so you can compute the symmetric of one or the other. Now, from the definition, it doesn't seem to be something particularly useful, at least it's not easy to understand what this can be used for, but this is very used, for example, for linear time invariant systems, which are something, for example, imagine that we had an iron bar here that we could hit with a hammer. And this would be the response of the bar, the oscillations of the bar to that impact. This is a linear system if we assume that increasing the strength of the impact would linearly increase the oscillations of the bar. And it's time invariant because it doesn't matter when in time we hit the bar, the pattern will appear after we hit the bar, regardless of when we started to count the time. So this is an example, and let's suppose that we wanted to know what would be the oscillations of the bar, or the result of the function, if we hit it twice with the hammer very fast. Now, hitting it once makes the oscillations look like this, but if we hit again at 0.2 seconds when it's oscillating this way, what would happen? What would be the change there? And so what we can do is to take the symmetric of the response, for example, and then compute the convolution of the two functions at different times. So this would be using different time shifts for the symmetric of the response, and this is the result of the product of the integral of the product of those two at different time shifts. And we can see that before the time of the hammer strike, the convolution is 0. There is nothing there because some terms on the product are 0. And then when we hit with the hammer, we start having this convolution here. So basically, the convolution operation allows us to figure out what would be the oscillation of the iron bar when we hit it with these two hammer strikes. For our purposes on convolutional networks, we can think of this in a different application, which would be to find patterns. Imagine that we have this signal, for example, we are listening on the radio or something like that, and there is a strange pattern that sometimes occurs, and we want to know when that pattern occurs. So we could create a detector function for the vector, and now we compute the convolution shifted at different time positions, so at different values of time. And the convolution will be here. If we are looking for the pattern over here, we have a very small value for the convolution function, but when the pattern matches the signal, we have a peak on the convolution here. So looking at the convolution of those two functions, we can figure out exactly when the pattern is superimposed on our detector, or when our detector detects the pattern. And this is what we are going to do with the convolution layers. The thing is that the detector is actually something the network is going to learn. It's going to learn a set of values that categorizes the detector, and then it's going to scan the input in order to detect those particular patterns. So this is for continuous functions. We use the integral. If we have discrete vectors of values, instead of the integral, we can consider the sum. We can consider the sum over from minus infinity to infinity, but if we have a narrow interval where we have those values, so if we have finite vectors, we can also imagine that they are zero outside the vector, and so only those values inside will matter. So basically what we're going to do is we're going to create this kernel, this set of values that is going to multiply by the input in order to detect meaningful patterns. So since the input is finite and discrete, we can assume that everything that is outside the input will be zero, and the same thing for the kernel. So even though this has in theory a range of infinity, we can just consider the dimensions of the input and the kernel. And the output will be a tensor that in general we're going to see some details, but it's approximately the same size as the input. So we have a vector of values x here. We are going to apply this kernel w to multiply element by element, and then we're going to obtain something that has the same dimension of x. So suppose that x was this vector here, and we could obtain this vector here as the output, which tells us where the detector found the relevant pattern. Now, we usually use convolution in more than one dimension. We can use it in one dimension if we have things like sound waves, text documents, things like that. We can look at that time dimension, but we can use it in two dimensions if we have images and we are looking at that plane. We can use it in three dimensions if you have, say, a CAT scan that is a three-dimensional representation, or MRI or PET scans can also be three-dimensional. So if you have that kind of data, you can use these convolutions in n dimensions. Now you can use either the coordinate system of the image and then move the kernel there, or in this case use the coordinate system of the kernel and move the image with respect to the kernel. Since convolution is commutative, we don't really care, and generally we consider that we are placing the kernel in a particular position of the input. So we have for the value of the convolution at coordinates I and j, we consider that we are placing the kernel at coordinates I and j of the image. And then we follow these coordinates on the kernel and the modified coordinates on the image. And also, since the direction is only for the commutative property of the convolution, so this inversal that we do here on the coordinates of one of the functions with respect to the other, and if we are learning the weights, this doesn't really matter, because note that if we are using these coordinates inverted, if we just flip the weights on the kernel, we can use the same direction in the input and the kernel. This, in fact, mathematically is not really convolution. Now it's a cross correlation because it's no longer commutative and so on, but we don't care about those mathematical details. We are basically learning this kernel that multiplies the input and outputs something that is like the input, but gives us the values where the kernel detected the patterns that we want. So we call that the feature map that gives us the positions of where the patterns were found. So let's see how we can do that with a convolutional neural network and what advantages we have here. There are basically three advantages. The first two have to do with minimizing the number of parameters, because we have sparse connections between the layers. and we share the same parameters over different neurons conceptually, or we just use one neuron to scan the input. It's the same thing, but the idea is that we need fewer parameters because of that. Another important aspect is that there is an equivariance between the input and the output on a convolutional layer. That is, some kinds of changes on the input provoke the same changes on the output. I'm going to talk a bit about these three in more detail. So one is sparse interactions. Suppose that you have a dense layer connected to some input. Each neuron on the dense layer is connected to all the values of the input. In general, in a convolutional layer, we have a small receptive field, and each part of the convolutional layer is only looking at a small part of the input. So this position here, or this neuron here on the convolutional layer, is only looking at these values on the input and ignoring everything that's outside the receptive field. So this way we can reduce the number of parameters we have in a convolutional layer when compared to a dense layer. Note, however, that as we stack convolutional layers, we can actually have neurons or positions on the convolutional layer that are receiving a wider field, a wider receptive field on the input, because this works like a pyramid. As we go deeper in the network, we are receiving the outputs of previous layers that were looking at previous layers and so on at increasing the receptive fields. Another aspect of convolutional layers that reduces the number of parameters we need is the sharing of parameters. If we have a dense layer, all of these connections have different parameters. They can all be trained independently. If we have a convolutional layer with this receptive field of 3, we can imagine that this is a kernel that is scanning through the input. Or if we imagine that they are very different positions and different neurons, then this weight is always the same in all of them. Because this works as if we had one neuron that was going through the input, always using the same weights. So instead of having 5 different weights here, we have the same parameter for all of these connections, because it's always the same neuron looking at the input in different positions. This can be also has this property of equivariance, because when we are scanning through the input with the same neuron, we are obtaining a feature map that shows us where some pattern occurs. So for example, suppose that we have a very simple kernel that just takes the difference between the pixel on the left on the right and subtracts the pixel on the left. So if we go from white to black, we have a low value. If we go from black to white, we have a high value, and we get this feature map here that shows us where there are these transitions between the two colors. If we change a bit the position of the dog here on the image, this will result in the same feature map, but just changed a bit to the side or up or down. So this is the property of equivariance, where we don't have everything changing just because the input shifted a bit. It doesn't work for rotations, because we have the same matrix being translated, the kernel being translated across the input, but it works for translations, and this means that shifting the input will just shift the feature map corresponding. So these are big advantages when we have to deal with unstructured data that has patterns that can occur anywhere along the input. So if you are looking at a sound file and trying to find specific words, or an image and trying to find specific objects, things like that, then using convolution networks is good, because these convolutional layers search for the patterns anywhere in the input. So one property that each of these neurons have, if we imagine the convolutional layer to be composed of neurons that scan through the input, each neuron will have a receptive field that is the part of the neuron, the size of the input, where it's actually looking at each position as it scans through the input. The name receptive fields come from the visual cortex because neurons in our visual cortex only receive input from small parts of the retina. And so different neurons are specialized in different parts of the retina. And generally, we have used multiple convolution filters which have each their own set of weights. So each one has its own kernel with different weights. And this is how things work in practice. Imagine that these numbers, small numbers here in red, are the kernel, so the weights of the neuron. And it's going to be applied to different positions on the input, always with the same receptive field. And what we're doing here is we are multiplying each weight by each corresponding value and then adding all of these together. This is exactly the same as all neurons. You have that sum of the products of the weights and the inputs. But this is going to be done only for the receptive field, and then we compute the value for that particular position. So here we're going to have a feature map, which is the result of all these convolutions applied to different parts of the input. And now we can have several of these, so we will obtain several different feature maps, a stack of feature maps. So this is how this looks like in tensors. Suppose that you have a color image here. The image has a height and a width, and since it's a color image, it has three layers, red, green, and blue, to define the mixture. That mixture defines the colors. So this is a three-dimensional tensor that represents one input. And now we have neurons here that are going to scan through the image, and for each position they're going to look at the receptive field and all the layers of the image, so red, green, and blue. And they are going to generate one feature map. So each neuron generates one feature map that also has height and width, like the image. But if we have several neurons, we have several feature maps stacked. And the depth of this tensor will be the number of filters that we are using here, the number of neurons we have on that layer. And now we can use this tensor into the next convolutional layer and so forth, and then stack these convolutional layers. Since the convolution itself is a linear transformation, when we create the convolutional filter, we have the kernel, which is the matrix of weights for that particular neuron. The product of each weight and the corresponding input, all of those are summed to get the linear part of the neuron, that is the convolution. But then we need a non-linear activation. So generally we put the rectified linear unit or something like that, and everything together is called the convolutional filter. So one neuron with the activation that is scanning through the input and producing one feature map. Of course, we then put several filters on the convolutional layer, and we get a stack of feature maps. Okay. Now, for each convolutional layer, or in reality, for each convolutional filter, but usually we define a layer with the same set of parameters, we have this depth, which is the number of filters we're going to have on the layer. But also for the convolutions, we need to define the stride and padding. Stride is how we are stepping through the input. For example, here we have a convolution with a stride of 1, which means that at each iteration it's moving one cell at a time. Here we have a convolution with a stride of 2 that is jumping 2 cells at a time. So if you use a higher stride, in fact, the output will be smaller than the input because you are skipping some positions. Padding is what you can add at the outside of the input so that you can preserve the dimensions. We can see here this first example where we have an input of 5 by 5, but since the kernel cannot step outside the input matrix, the feature map is only 3 by 3 because this is the number of positions we can put the kernel in without going outside where there are no values. If we wanted to have a 5 by 5 output here, we could add padding, which is these zeros around the input, so that the kernel can move in all the positions it needs to generate an output with the same size. So this is something you can also specify padding, so that if you the feature map that you get has the same dimensions as the input that you're putting into the layer. This is an example of a convolutional network for classification. You're going to do one like this on the tutorial today. And basically we have convolutional layers here with rectified linear unit, then another one. This helps the deeper neurons capture the patterns from wider regions of the image. So the first convolutional layer, if it has a small receptive field, will only be able to capture patterns involving a small number of pixels. But then the second convolutional layer is looking at the feature map the first convolutional layer generated. And so it's now looking, even if it looks at a small receptive field on that feature map, this corresponds to a larger field from the previous layer. And as we go deeper into the network, these feature maps can be capturing patterns of larger and larger regions in the image. But in addition to this, we also have pooling to further reduce the resolution of the image and so increase the range in which the even small kernels can capture those patterns. And pooling is basically doing an aggregation of the inputs into the output in ways, for example, taking the average or the maximum value and so on. And these are usually interspersed between convolutional layers so that we can start to abstract from the position where the patterns occur to just the detection of whether or not those patterns occur. So we reduce the resolution of the input and we reduce the dependency on exactly where the patterns are occurring. So let's see an example here of max pooling. We are doing here max pooling of windows of 2 by 2 and with a stride of 2. So if the stride is also the size of the window in which we are pooling, we don't have overlaps between the different pools and we reduce the size of the input. So here we are doing max pooling, which means that we take the maximum value, for example here in this orange region, this is a 6, this green one has an 8, and so on. And basically, suppose that this 8, this high value, indicates that this pattern was found there, the pattern corresponding to this feature map. So now, here we knew that the pattern was found exactly in this position, but now we know that it's somewhere around here. We don't particularly care where. So we can start reducing the size of the inputs, keeping the information of which patterns we found, but discarding the information about exactly where in the input they were found, because that may not be relevant for our purposes. Typical pooling functions are max pooling, average pooling, L2 norm, and so on. So these are just 3 examples, but the idea is to make this aggregation of the values and so reduce the size of the input while keeping information about which patterns were found. We may want to create pooling with some overlap, but in general we do pooling, for example, 2 by 2 in 2 dimensions with the stride of 2 to just reduce everything by 2 and have no overlap in the different regions of pooling. And we can do this in this way. This is what we're going to do today, which is add these convolutional layers and pooling. We are abstracting from the exact location of the patterns, but keeping the information that we found the patterns, and then we flatten everything into a single vector at the end, and pass on to fully connected layers, to dense layers, so that we can do classification. So this is typical, the typical architecture of convolutional networks for classification. We have a part of a stack of convolutions, and then we add some dense layers, 2 or 3 dense layers, just to do the classification based on the features that were detected by the convolutional layers. But there are cases where we can have fully convolutional networks. So this is another example of a classification network that has these dense layers here. So this one is convolutional at the beginning, but then it's a dense network. But we can have networks that output a feature map at the end. So this can be convolutions all the way. And we have here in this example, this is a network for image segmentation. Instead of just telling the class of the image, it assigns to each pixel what it belongs to. So there are pixels here for the dog and the cat and the couch and so forth. And what we are doing here is stacking convolutions and pooling, and then doing an upsampling to get, again, something that looks like an image, but now it's an image with only a few different colors, a few different labels that indicate which category each pixel belongs to. So this is an example of the use for fully convolutional networks, which is for image segmentation, for assigning each pixel to a different type of region in the image. We're going to see next week, also with autoencoders, another example of this, and discuss a bit more this stage where we go from low resolution to high resolution. But this is just to give you an idea that convolutional networks can be part of the network, so the convolutional layers is only part of the network, and then we move on to dense layers for classification, or they can make up the whole network if we have different applications. Okay, so now to do this, we are not going to implement this at a low level of TensorFlow because that would be also more complicated than the examples we saw so far. We are now going to start working at a higher level using the Keras API. And first we're going to use the sequential model. So basically you need to import some optimizer. You can use the same we've been using, or you can try the ones I talked on the previous lecture. And we're going to import from the Keras models this class for the sequential model. So basically the sequential model is the lasagna of deep learning, where you just stack things one on top of the other. And if you don't need to do anything more complex than that, sequential model is very easy to use because you just add layers there. And the kind of layers we're going to use is batch normalization. This is the one I talked previously, that we are standardizing the outputs of one layer before feeding into the network. In the next one, this speeds up learning. Convolution in 2 dimensions, which is the convolution we're going to apply to images. Max pooling in 2 dimensions to do pooling, and then we can have this activation if you want to separate the layer itself from the activation function and just make things more explicit and see where they appear. Flatten to pass from convolution to the dense layers. Drop out to implement that regularization method we saw. And the dense layer is the kind of layers that you've been implementing so far. This has this dense classic character. So the way you use this is you start by creating the model. So this is an object of the sequential class. And this object has an add method that allows you to add layers. You start from the input and you keep adding layers until you reach the output. The first time you add a layer, for example, let's add a 2-dimensional convolution with 32 filters and a receptive field of 3 by 3. We also use a padding of same, which is that padding of zeros around the input that allows us to keep the same size of the input in the feature map, so it preserves the dimensions. And for the first layer that you add, you need to add this argument of the input shape. We're going to use this with the fashion list, and these are images that are 28 by 28, and they only have one channel because they are grayscale images. So the shape of each example that is going to be presented to this convolutional layer is 28 by 28 by 1, and the reason why we need a 3-dimensional tensor is because this could have several channels. It could be a color image, for example, with 3 channels for the color, or it could be a tensor coming from another convolutional layer and have lots of feature maps. For example, since this convolutional layer has 32 filters, the tensor that is going to be output by this convolutional layer will have a depth of 32. So with these parameters, the output of this convolutional layer will be a tensor of 28 by 28 by 32 of depth, because we have 32 feature maps being trained on this input. And now we can add an activation, or you can also add the activation as an argument there if you prefer, but this is just to illustrate this layering of creating the network. And then you can do other convolutions, activation, and so on. Eventually we're going to do pooling, so this is an example of maps pooling. The pool size in this case is 2 by 2. By default, the stride is equal to the pool size, so it will shrink the dimensions by 2 in width and height. And then we add convolutions and create, there are some parts missing here, but we create all of this part of the network that has convolutions. Now note that we needed to specify the input shape on the first layer, because the sequential model needs to know what is the shape of the data we're going to feed into the network. But we don't need to do that anymore, because now each layer, the input shape depends on the previous layer, and the sequential model handles that automatically. So you don't need to worry about specifying that. Eventually, we reach the dense part of the classification. So, since we are moving three-dimensional tensors along the convolutional layers, because each convolutional layer generates a three-dimensional tensor for each example, when we move to the dense layers, we need to convert this into a single vector. And so we use the flattened layer there. This just converts an n-dimensional tensor into a one-dimensional vector, and then we feed that into a dense layer with 512 neurons with a rectified linear unit activation. And here, for example, we can add batch normalization and then drop out to reduce overfitting, and a dense layer at the end with a softmax activation for classification. So in this particular example, this is the one we are going to do on the tutorial. There are 10 classes. So we have 10 neurons with a softmax activation. Yeah.
Shouldn't we do the batch normalization between each step?
Yes, you can use batch normalization here also on the convolutional layers. You should not use batch normalization after dropout. This messes a bit with batch normalization, because dropout between training and inference needs to rescale the weights or the activations of the neurons depending on the type of dropout. And batch normalization keeps track of the averages and standard deviations during training. So if after training you rescale things, but batch normalization is still using the same parameters, it will not work well. So in theory, you could do something more sophisticated that join the two together, but if you are using these layers, it's not a good idea to use batch normalization after dropout. So basically, you can use batch normalization here, then use dropout on this part. Also, dropout on the convolutional layers is a bit strange, because you're dropping out old feature maps and so on, so it doesn't work that well. And generally, convolutional layers have very few parameters compared to dense layers. So usually we use dropout only on the dense part. So basically, this is what I've been talking now. Batch normalization after activation. Also, this is important, because one way of thinking about this is that batch normalization is that step of standardization before feeding the data into the network. So it should be the last thing before finding the new layer. So after the activation of the previous layer and all other things that you may be doing. Dropout only after all batch normalizations, or don't use batch normalization after dropout, because the rescaling that it's going to do will mess a bit with how the two combine together. And dropout is generally not that used in convolutional layers. They don't have so many parameters. It's better to use dropout on the dense part of the network. Okay, so here is an example how we can do. We start by creating an optimizer, then we create the model. Basically, this create model function will be the function where you implement all of this. I recommend doing it in a function that returns the model, because then you can import it from a different module if you want to reuse that model. And now we train the model, and to train, you just call the fit method after compiling the model. When compiling, you can specify the optimizer and also additional metrics and the loss function that you're going to use. So for this particular example, we have a classification with the 10 different classes. We're going to use the categorical cross entropy and the softmax activation on our network. And since it's a classification problem, we can add accuracy as a metric. So accuracy is the fraction of examples that were correctly classified, and this makes it easier for us to track, to follow what the network is doing at the performance. So to train, you just need to call fit. You give the input matrix for the network and the target labels. So this is the training set here. You can also include validation data so that you get a report of the validation losses. And you specify the batch size and the number of outputs, and the fit will train and return an object that has all the information about the loss functions that you had and the metrics during training. This save weights method allows you to save the weights, all the parameters of the network to a file, so that after training you can then reload this and not have to train the network again. So today it's important to do this because we're going to use this network again next week for transfer learning. After you compile, so after doing this, you can do summary and you get an output of what your network looks like, what are all the layers and the sizes of the layers, the number of parameters and so on. You can also include callbacks for TensorBoard. For example, you can create here a log directory for your run, and then create this callback so that you can look at things in TensorBoard. So this would be the folder where this particular run will be stored. Note that if you just call it logs, then if you run again, you have to delete what you had there or change the name here. If you want the folder to change automatically, use here the same trick we saw previously of creating a folder with the timestamp. But in any case, you select where you want this particular run to be stored, and then you can put the callbacks here. When you call the fit, you can put these TensorBoard callbacks. The callbacks on Keras can be used for lots of things. So basically, these are these allow you to do something during the training of the network. This is just an example, which is logging things to TensorBoard. But if you want to create your own callbacks, for example, to dynamically adjust the learning rate or to stop the network training when you reach some loss value, or if validation starts to increase, things like that, there are callbacks for many things, and you can create your own too. After you fit, you can either monitor this in TensorBoard, or in any case, after the fit ends, it returns this history object that has a history field that is a dictionary with the values of all the things that have been measured during training, which include, in this case, since we have validation data, will be the loss for the training set and the validation loss. And since we added here when compiling the model, we added this accuracy metrics, we also have the accuracy and the accuracy for the validation set. So then you can do the plots if you want with these values. Okay, so today we're going to apply this to the fashion list. This is a data set that is similar in size to the MIS. This is also grayscale, 28 by 28, but it's a bit harder to classify because instead of the digits you have these cartoons of clothes, but it's the same shape. It has 10 classes and grayscale images of 28 by 28, and you can use it in a similar way as you use NIST. So you go to the Keras datasets, fashion NIST, and load data. And now we're going to reshape things a bit differently. Last week you used the dense network to try to classify NIST. So each example was one vector of 768 values. Now we're going to use convolutional networks. So to put this in a two-dimensional convolutional layer, we need a three-dimensional tensor because we need to have the height and the width of the image and then specify how many layers we have there, how many channels in the input. So since this is a grayscale image, it only has one channel. So this is the shape of each image that we're going to have. We're going to convert this to float 32, and also remember from last week we have the labels 0 through 9 for the different classes, but since we have a softmax activation with 10 neurons, we are trying to train the network to give us a vector of zeros on all the wrong classes and with a 1 in the right class. So we need to use this two-categorical function to convert the integers into the one-hot encoding, those vectors that have zeros and ones, just like we did last week. Okay? So this part is similar to what we did last week with NIST, only you are using fashion NIST, and the shape of the images is actually a three-dimensional tensor and not just one vector like we did last week. Okay, so now you build your network. I propose doing something like this. So start with two convolutional layers with 32 filters each and rectified linear unit activation with patch normalizations. Then do a pooling and then add another of these stacks but with 64 filters. Then do pooling again. Optionally, you can try to put dropout there in the convolutional layers, but this will probably not give an improvement because you are mixing dropout in convolution and you're putting dropout with batch normalization and it will mess things up a bit. So generally, dropout will work better in this network just at the end. So after you put these two stacks of convolutions and pooling, you can flatten things and pass on to that layer of 512 neurons. And here you can use dropout for this dense layer, and then the softmax layer with 10 neurons for classification. If you want, you can change this a bit, add more layers on the dense part, for example. Doing more pooling may be a bit risky because you have images of 28 by 28, so when you do the first pooling, it's 14 by 14. Then the second pooling, it's already 7 by 7, and it starts to become very small. But you can experiment with this if you want. Experiment with different optimizers if you want, and run this, look at the classification, accuracy in training, and validation to get an idea of how things are performed. Just remember at the end to save the weights. So after you train here or at home, do this, because next week we're going to reuse this network for transfer level. Okay, so to sum up, we saw what convolutions are. We saw convolutional networks, both for classification, which tend to terminate on dense layers for the classification, and fully convolutional networks that can be used, for example, for image segmentation, where we want to assign class to each pixel and not to just to the whole image. And we saw how to build these networks with the sequential API. Next week we're going to look at the functional API, and today, if you want, we can talk a bit about the first assignment. I'm going to put the instructions there during this week, but it's relatively simple. You need to do a tutorial. We can discuss that a bit now.